Hi, my name is Erich Spengler, and we're going to talk about VLSM and right sizing your network. Now, let me explain a little bit about what I have here on the board. What I have is a typical network, which includes 4 routers and 7 networks. These networks vary in size from 30, 20, 10, and 2 hosts. What we need to do, or as a goal, is to be able to take a network prefix and apply a solution to this network by splitting this network prefix into multiple pieces. And we're going to be doing this in the context of using a VLSM. Now, when I teach my students, I spend a little bit of time with those students teaching them the concepts and the differences between classical and VLSM. And we don't have time for that today, but we're going to jump right in and talk about the approach to better understand the application of VLSM into a network. So let's take a look at our requirements quickly. What we've done first is we've taken our network requirements, which is our host requirements, and we've sorted them in order. And the reason why this becomes so important is because this defines our requirements. And when you're doing subnetting and trying to teach your students subnetting, we break it down into 3 pieces. And that is take, of course, what you're given, but then take your requirements, define your requirements, and then solve for your mask and your network ID. Now, classical subnetting is that approach where we take and we apply even length subnet segments from a prefix into a network solution. Now, many of you have already experienced classical subnetting, and in fact, I try to reduce the importance of classical subnetting to my students, because what I found in many cases is if you try to teach classical subnetting and then you teach VLSM, sometimes they get confused. So I like to jump right into VLSM quickly so they understand the concept of right sizing your network is the way we work in today's world. So let's take a look what we did. Aside from classical, and an observation that we have is that within classical, we ran out of space. We didn't have enough addresses to allocate and solve that problem. By right sizing your network, you're taking the masks and you're taking the network IDs and you're only applying what you need. And again, a best practice approach that I use is to sort our requirements, greatest to least, pick a mask that best fits and represents the number of hosts that's required for that requirement and that need, and then apply a network ID that solves the problem within my prefix. So in this case, what I've done is I've applied 224, 224, which gives me a group of 30 hosts, 240 and 240, which gives me a group of 14 hosts, and then 252 in each of these will give me a group of 2 hosts. So I haven't picked out my networks yet, but what I've done is I've determined this process and this need will solve my problem. From this point on, it's simply applying the network IDs from the prefix I've been given. So if I need a block of 30 hosts, it's a 32 block within my prefix. So it's .32. I can take the first one, .64. Okay? And then, of course, that'll take all the way up to 95. Now I go to .96, but I don't need to go .32 because I'm using a 240 mask. So it goes to .112. And then, of course, I don't need to keep going because it's VLSM. So I can go and I can pick those pieces out as long as they're not overlapping with other sections. So I've actually gone back and I'm backfilling the address space that I have. So I'm using .4, .8, and .12. So I've just solved this problem, and one of the things you can note certainly is that not only have I solved this problem by right sizing my network, but comparing it to classical, I've run out in classical, and in this case, I've only used 50% of the available host IDs that I've been given. So I could double the size of my network, and I can still have enough to continue within that prefix.